Heat and internal energy. Internal energy includes kinetic energy of molecules, vibrational potential energy of atoms and molecules, and all kind of electric potential energy associated with forces between molecules. Kinetic energy of the system itself due to its motion through space is not included in internal energy. Heat is a process of transferring energy, and that process happens because the temperature between system and surrounding different. It's also the amount of energy transferred by this process. When you heat a substance, you're transferring energy by placing it in contact with surrounding that have a higher temperature. Heat, quantity of heat, is associated with the name of James Prescott Joule, English physicist. Heat is energy absorbed or lost by a body due to a temperature difference. Energy in transit. The unit SI unit are joules. For our units, calorie, which is 4.186 joules, and kilocalorie, 1,000 calories, and these are calories on the food level. The calorie, which is defined as the amount of energy transfer necessary to rise the temperature of 1 gram of water between 14.5 to 15.5 degrees of Celsius, 1 degree of Celsius. So the unit of energy in US customary system is the British thermal unit, BTU, which is defined as amount of energy transfer required to raise the temperature of 1 pound of water for 1 degree. So if Q is larger than 0, heat is absorbed by a body. If it's less than 0, heat leaves the body loses heat. And we will see several expressions for Q. Conservation of energy, also known as calorimetry, is attempt to try to isolate system and doesn't lose heat. When an isolated system, the algebraic sum of all heat exchanges within a system has to be so equal to 0, because the system doesn't lose energy. Let's consider equivalence between mechanical energy and the internal energy. So there is a little device which Joule was discovering. So the falling blocks rotate the puddles, causing the temperature of the water to increase. The decrease in potential energy of the system as the blocks fall equals the work done by the pedal wheel on the water, and in turn the increase of internal energy of the water. Joule found that the decrease in mechanical energy is proportional to the product of mass of water and increase in water temperature, proportional to the mass and to how many degrees the temperature increased by. So, and this is now a way to say, it's now a way to introduce a heat capacity. Heat capacity, C, for a particular sample is defined as the amount of energy needed to raise the temperature of that sample by 1 degree. Absorption of heat. The amount of heat the body absorbs is proportional to the mass and proportional to the change of the temperature. So Q is the heat energy required to change the temperature of material by delta T. And C, called heat capacity, specific heat material, treat as independent T. Units are joule divided by kilogram Kelvin. Specific means that the proportionality to mass is factored. Let's look at the video about the water in a balloon. We're back. So let's talk more about absorption of a heat. So as I said, Q is mc delta T. Now, if delta T is really small, we talk about a very small infinitesimal um, amount of heat. So write everything in differential form, and then solve for C. So C, the specific heat, would be 1 over m dq dt. So it's a derivative of a q with respect of time. If q and t, and if change of q and change of t is positive, so heat absorbed by m, and if it's negative, each of them negative, heat leaves m. Phase is a state of a matter, example solid, liquid, or vapor. Energy is needed to change phase of matter. Under phase transition of matter, only its phase changes, not its temperature. The phase change doesn't, during phase change, we don't change temperature. Now, that's example of phase change in water, so pay attention, it's temperature degrees Celsius. So you heat the water and it starts to warm up. You start with ice, you warm up, and at point B it's transfer to a liquid phase, and you see temperature doesn't change then. Liquid phase, and you go to liquid phase. During a liquid phase between 0 and 100 degrees of Celsius, the temperature increases, and then from point D to point E, the water boils and temperature doesn't change, and then the steam, all water becomes steam, and then again temperature can increase. So solid liquid phase change, in order to change the phase, you need to supply or absorb some heat. Of course, it's proportional to the mass of the sample. So, and of course, per unit mass, that is necessary heat per unit mass, called the heat of fusion or latent heat of fusion of a material. So it's measured in joule per kilogram or in joule per gram or any other units. Plus is for melting, and the minus is for freezing. So liquid vapor phase change is basically the same story, but the latent heat is of a vaporization apparently is different thing, different number. So plus for evaporating and minus for condensing. So let's talk about heat transfer. dq dt is a rate of heat flow, heat current, right? Heat current. So it's a measure the rate how fast the heat flows. There are three mechanisms of achieving heat transfer: conduction, convection, and radiation. So conduction is done by collisions of molecules, and we don't consider bulk motion. Convection, you have a bulk motion from one region to another, and radiation is just emission of electromagnetic waves. Conduction is done the following way. So you have the object with a higher temperature. So you have an object with a colder temperature. You have a little tube through which the process conduct, but the walls of these tubes are isolated, so there is no loss of energy. Now, of course, there is length of this tube, there is a constant area, section area, and well, there is a heat current. So what this heat current is proportional to? The bigger area, the more heat current is. The longer tube, the less heat current is. So the current is going to go slow. And the most important is proportional to difference of temperature. The K, a coefficient, is a thermal conductivity of material. So A is a cross section, as I said, L is the length of material, and the conduction goes with this formula, right? So convection is a little more complicated. So you can see two pictures which you probably saw from grade school or kindergarten. So when it's daytime, the cooler air over water moving towards the land goes up, cools down, goes down, and so on. And at night is opposite convection, and also you could consider other ways of convection. It's a very complicated process. We're not going to talk much about this. Radiation, for example, emitted by the sun. So suppose you have a spaceship and it's got its energy from radiation from the sun, for example, using solar panels. So radiations are electromagnetic waves. For example, visible light is located here, so there are shorter waves, there are longer waves where the radio is. It's not what we're going to talk about much in this course, it's in the next course. So, but I'm going to mention very interesting thing, that the heat flow is actually proportional to a fourth degree of the temperature of the source of this radiation, fourth degree. All bodies emit electromagnetic radiation, and area is the surface area of a body, T surface temperature of a body, and E is emissivity emissivity of a body. It goes from 0 to 1 and actually associated with the color of a body. Absorption of radiation, kind of opposite to emission. In general, body emits radiation and also absorb radiation from their surroundings. And sorry about that. So if T is the surface temperature of body and the T as the surface of a surrounding, of course, the net flow is emitted minus absorbed. So let's talk more about heat capacity. Now, that is formula which we use to divide a specific heat capacity, right? C is specific heat capacity. Sometimes we call it heat capacity by mistake, but it's specific because we factor M, right? It's per unit of mass. So energy required per unit mass and unit temperature. Now, I would like to show you a fantastic video, specific heat of metal.
Now we're going to look at specific heat. Specific heat is defined as the amount of heat required to raise 1 gram of a substance 1 degree Celsius. For example, water has a specific heat of 4.184 joules per gram per Celsius degree. We have a piece of cadmium metal, and we're going to try to find out the specific heat of this metal. We know that the quantity of heat is equal to mass times the specific heat times the change in temperature. So let's start by finding the mass of our sample. The mass of our sample is 58.953 grams. What we're going to do is we're going to heat this sample to 100 degrees, or approximately 100 degrees. We'll get the exact temperature. And we're going to take 100 milliliters of water at room temperature. So let's measure 100 milliliters of water. Remember that 1 milliliter of water is 1 gram. So if we know that we have 100 milliliters, then we know that we have 100 grams. And this is at room temperature. So we know that when we put this hot metal in there, it's going to gain heat. We're going to use our coffee cup calorimeter because it's insulated. And we're going to assume that it gains no heat and the water gains all of the energy that's given off by our metal. So let's find the temperature of our water. And the temperature is 22 degrees Celsius. And we have our water boiling, so we're going to tie a string to our sample so that it doesn't touch the bottom of the beaker. If it touches the bottom of the beaker, then we don't know for sure what the temperature is. But if it stays in the water, then we know that the metal will be the same temperature as the water temperature. So let's put our thermometer in the water, about the same height, and then we'll lower everything in the water together. And we're going to let this boil long enough that we know that the temperature of the metal is the same temperature as the water. I think we've waited long enough to be confident that our metal and our water are at the same temperature. Our temperature is exactly 100 degrees. So I'm going to take out my thermometer. And I'm going to take my sample. And I'm going to quickly put it in the water. Put the top on. Swirl it around. And going to swirl the cadmium metal in the water with a thermometer to try to make sure that we get uniform temperature. We'll read our thermometer, and when it stops changing, we'll record that temperature. And it looks like it's steady at 25 degrees C. So that means we have a 3-degree temperature change. So you now have the temperature change in the water, the temperature change in the metal, and the mass of the metal. So your task is to calculate the specific heat of our cadmium metal.
The video ended up with a question. Please look at the question. You can pause the video and try to solve this. So what do we have? We have a water which is warmed up. We have a cadmium which cooled down 75 degrees. And apparently, since things were isolated, insulated, isolated and insulated, so heat didn't go anywhere. So the heat needed to warm up water should be equal to heat needed to the heat the cadmium lost. Right, let's try to calculate the heat which water gained. It's 100 grams, 4.184, that's the specific heat capacity which the lady told us, and the increase is 3 degrees Celsius. How much is that? That's 1255.2 joules. Okay. And that has to be mass by capacity by delta T for cadmium. Delta T for cadmium 75 degrees, and the mass of cadmium is almost 59 grams. And see, that's what I would like to find. Well, if you solve this equation, you have 0.27710. The actual, more precise, the specific heat capacity for cadmium is actually not that much different. It's 0.23 joule per gram per Kelvin. Okay. We are very successful. So now let's introduce a molar heat capacity. Well, it's not very complicated. It's energy per mole per unit delta T required to change temperature of n moles by delta T. So instead of mc, you have n capital C. That's your molar heat capacity. So when I say molar heat capacity, I probably would move to gases. And important case is the volume of V of material is held constant. So the volume of material held constant, the CV is a molar heat capacity, the constant volume. Right, so for ideal gas, what we have here, we have the molecules of gas moving, and we can measure temperature. If you heat the gas, well, temperature rising because of kinetic energy increasing. Now, monatomic gas consisting is only one atom. Molecules are point-like, and transitional kinetic energy of gas averaged over all molecules is 3/2 nRT. So this formula, which is not necessary for this course success, is covered in the previous PowerPoint, which I put on Canvas. So you're welcome to look at details. And once again, this is for monatomic gas. Your text, just write TR transition instead of average. So actually it's average kinetic energy. Now if you change T by delta T by dt, so you would have the infinitesimal change of kinetic energy would be just d would transfer to t because r is a constant, n is a constant, and 3/2 is obviously a constant. So we recall that dq is ncv dt. So, well, by comparison, you see cv is a 3/2 of constant r. In general, story is a little bit different. If you have a more complicated structure of a molecule, so the total average energy is F over 2 nRT, where F is degree of freedom, whatever that means. We're going to talk about more. So, and the same calculation allow us to introduce a molar heat capacity with constant volume as F over 2R. So apparently in previous case that was F equal to 3. The atomic gas actually has all kind of different CVs. Can have 3, can have 5, can 7. We're going to talk about that. Now, what about gases with other kinds of molecules? That's what I'm trying to say. Diatomic, triatomic, and so on. These molecules are not point-like. For diatomic gas, they look like dumbbell shape. Its energy takes several forms. It has a translational kinetic energy, 3 directions, so 3 degrees of freedom. Rotational kinetic energy, 2 rotational axes, 2 degrees of freedom. And vibrational kinetic energy and potential energy, which is another degree of freedom. So the atomic gas have all kind of combination of total energy. So, and we know that average kinetic energy is 3/2 nRT. And what about the other terms? It can be proved, but we just use the result and we don't want to prove. The F is a number of degrees of freedom. It's a number of independent ways that a molecule can store energy. So it can be shown that the average amount of energy in each degree of freedom is 1/2 kT per molecule. So 1/2 RT per mole. So monatomic gas has only translational kinetic energy in 3 directions, 3 degrees of freedom, so it has F equal to 3, and the kinetic energy is 3/2 nRT. So the atomic gas have a little bit more, forms of energy available to the gas as you increase the temperature. If it's cold, you have 3 degrees of freedom. If it's warm up, it has 2 more, and then it has vibrational kinetic energy and potential energy, so 2 more. So, and here we have at lower temperature 3 degrees of freedom. At higher temperature 5 degrees of freedom, right? And even at higher temperature, you add 2 more, 7 degrees of freedom. And does it hold water? So is that actually true? So people did measure, and they noticed that in the atomic molecules, you could have 3, 5, or 7 degrees of freedom, and that's how it looks in the graph. So if you increase the temperature of a gas consisting of the atomic molecules, all of a sudden the properties of these molecules change. They actually increase from 3R over 2 to 5R over 2, and from 5R02 to 7R02. So we know there is no such a thing as ideal gas, and that's how non-ideal that thing is. The constant CV is actually not a constant. It changes. So for solids, we already talked about that. We imagined that the molecules consist of just little balls connected with another balls with little springs. So each atom as a solid can vibrate about its equilibrium position. Atoms undergo simple harmonic motion in all three directions, and kinetic energy has 3 degrees of freedom. So for each degree of freedom, you have basically mv squared, and you have 3 of those. Well, there is no preferable direction, so they might be equal. So potential energy has also 3 values, right? So how much we have? 3 plus 3, 6 degrees of freedom. And for this formula, you have 6 over 2, 3 nRT. That's what you have for CV. So CV is a 3R for solid. And here you have different materials which, with certain increase of temperature, they come to what was predicted as a 3R. So why do you have to wait that thing to be 3R? Well, because in a lower temperature, not all of the degrees of freedom are alive. They are kind of like frozen. So, but after room temperature, for example, lead is having a 3R. After the boiling water temperature, aluminum have a 3R, and the silicon and diamonds are a little slower. Silicon diamonds a little slower. So let's talk about phase change one more time. So during a phase transition, two phases coexist, but there are cases where all three phases coexist. It's called a triple point, and it has a specific temperature and a pressure. On a PET phase diagram, you have this specific point, triple point. So you have a sublimation curve, which is very complicated. Then vapor and solid, they interchange. You have like hard to see this kind of example, but dry ice does that. It goes from solid immediately to vapor. So vapor to liquid, that's also clear, right? And the solid to liquid is also clear, right? Fusion curve is where the to the left you have solid, to the right you have liquid. And pay attention, the higher pressure, more likely the object would be having a solid phase. So, and this is a PV diagram for a non-ideal gas. It's a PV diagram for non-ideal gas, which we saw before. So this is ideal curve, which look like a hyperbola. But since the gas is not very ideal, so it's while the pressure go down with a lower volume, it's all of a sudden start to become a liquid. And then you have a certain equilibrium between point B and A when the liquid vapor phase exist together. So liquid and vapor exist together. So I believe that's the end of the class. Thank you very much for your attention.